We've covered, I think, in our last session and in this session, probably 80% of the programming language Java visited at some point or other. It's quite a breakneck pace, but it's also an indication of the reasonably tidy nature of Java itself. It's not a specifically large language at its core. It's a simplification of its ancestor languages. So, for instance, C++ is considerably more complex. And even some derived or related languages have gone quite a good bit further in terms of their expansion. Thinking of JavaScript in particular, which is now much larger really in scope and complexity than Java itself. So if Java is first contact with you and you're finding it a little bit challenging, well, there's not an awful lot more really. And revisiting the lectures from this week and last week again might get you onto a reasonable footing for the remainder of the course. Of course, in languages like this, it's no longer the core language itself that is a challenge, it's the libraries, and particularly the libraries and frameworks we may be using for specialized application development. And it's one of those libraries we're turning our attention to now, which is the collections framework. It's part of the core JDK. It's a standalone library, but it's bundled with all Java environments. So, and it's heavily used by many of the frameworks that we use for specialized development in Java itself. So let's take a look at the collections framework. It's quite complex. We don't need to go in tremendous depth into the framework, but there is a range of core features you do need to be comfortable with. You're already using them in the labs to date, but we haven't really explained them in any sense, at least not yet. We're in a position now though to have a crack at it, particularly as we've got inheritance and interfaces under our belt, and hopefully it'll start to make some of what you've been doing a little bit more concrete. So the collections framework itself, well, it's effectively a library of data structures. Anybody who's come through standard computer science education will have covered data structures at some point in their undergraduate careers, learning how to build lists and sort arrays, binary trees, B trees, maps, hash maps, and a range of algorithms associated with managing those data structures. Well, they're fun to do, but often challenging to implement and specialized. And most programming languages we would expect now to implement good quality realization of these data structures. In Java, it's called a collections framework. So we don't attempt to build our own data structures really in production. We tend to rely on proven implementations for reuse, obviously. Uniform approach to these containers, obviously it boosts our productivity because we're not implementing core algorithms, and we're getting interoperability. We are interacting with other frameworks and libraries that are also built on these concepts. That's a bit of an eyesore, or an eyeful, should I say. That is a small snapshot of the current collection framework. In fact, I'm hiding a lot of classes and interfaces that are not visible here. We don't need to grapple with this or at this level. We need to look at considerably simplified vision of what the collections framework contains, and then build on that simplification to extend our knowledge just in sufficient areas to allow us to do some work. At its core, the collections framework is a set of interfaces, a set of implementations, and also a set of algorithms. Interfaces are, using the syntax we just explored, they are contracts or types that define a range of signatures. Implementations are classes that implement these interfaces. And there are also uses of implementation inheritance to further customize those implementations. The algorithms are usually bound into the classes that implement the interfaces, but there are also some general purpose classes collecting a variety of other algorithms that can be applied to different collections. The diagram we are most interested in, though, is this one here. And if we get this, then we're in business. There is an interface called collection and an interface called map and an interface called iterator. Almost all collections have a relationship with one or more of these interfaces. And the two primary ones, the ones in fact you've been using, well, you've used one of them, are also interfaces, the interface set and list. So if we want to get an understanding of collections, we need to tour these 5 interfaces first. And once we've got a basic understanding of those, then the implementations of these interfaces, the classes, should make more sense. So we'll start with a collection. A collection is a real abstract concept of what a collection of objects should be. It's an interface, so it's entirely abstract. There's no implementation, and it's quite a generalized view of what a container should operate, what behavior a container should offer rather. So, for instance, the interface collection has an add method, allowing you to add some object to the collection, and it has an add all method, which will add every element in another collection to the collection you invoke this method against. So the core features of a collection is that you can add stuff to it, and that stuff will be retained. You can also remove. So once you put it in, you can take it back out again. And if you put in a collection, you may remove everything from another collection if it is still in the collection that you inserted into. Other methods in collection, you can check to see if an object is in there. You can check to see if a set of objects or a collection is in there. You can find out how big the collection is. You can see if it's empty or not. You can clear out the collection, or you can clear out everything except those that are members of another collection. And lastly, you can ask a collection for an iterator. And this is a way in which we can traverse the collection. It's a pattern, a fairly venerable pattern now in computer science at this stage. This iterator is a separate interface, and if somehow you can acquire an iterator, you can invoke methods on the iterator to move around inside the collection. So typically you might be calling next, but you may also call hasNext to see if there is a next available. And when you're traversing iterators, you're often working with these two in tandem to guide your algorithm as it's proceeding, say, sequentially from one object to another inside the collection. Set, well, set extends as it is derived from collection, so it customizes the collection in some manner, and it obeys the rules of algebraic set. Set is a collection that can contain duplicates. Otherwise, all the other methods work as you would expect, but if you insert more than one method, more than one object twice, then you can expect only one copy of the object to be inserted. List doesn't have that restriction. You can have many duplicates and they'll all be individual separate objects. List also has the concept of positional access, so you can get the first, second, third, or last element. Set is not equipped with that capability. So you have a range view possible in a list. And list obviously leads on to what you've already used, which is an array list in your labs to date. Map is separate from collection, and we can see it's related to a collection in some unspecified way here, but map is effectively a dictionary, name-value pairs. You put something in, but you're not putting it in to the end or maybe as a unique element in the collection. you're putting it in at a given key position. So it's a key value store, effectively. Now, they are only interfaces. They're not implemented because interfaces are abstract unless you specifically choose a class that implements them. And the three primary classes that are most often used in collections framework would be hash map, which realizes a map. Array list, you've already seen this in action. It gives you a simple container for objects that realizes list semantics. And set, or hash set in this instance, which is a container for unique objects. And there are the three building blocks, really, that you can start to extrapolate most of the collections in that larger diagram I showed you earlier are derived or related to these in some sense. So a few examples. Array list. You've seen this in action. You can create an array list, add elements to it, find out what size it is, and at the bottom left here, iterate through the list, that is, visit each element, selecting or printing out each element in the list itself. You will notice here I'm doing something we thought we'd avoid, which is casting. So every time I proceed through the iterator, I'm casting the next object down to a string, because a string is what I originally inserted up here. And we'll see in a moment how we can make this code easier to read and more elegant by eliminating the need for casting. We'll park that notion for a second. A list then is quite intuitive. Put things in, get things out at specific indexes, if we like. And of course, then we can find out how many elements are in the array, and we can clear it and so on. Hash map, a little bit different. It's where we're inserting at a given key value pair. Ordering isn't critical. There's a more complicated data structure, and there are some more sophisticated ways of tuning the data structure for performance. If you've ever studied maps in data structures, then there are obscure features around called load factors to determine how efficient the map is. It's not really our concern for the moment. We're just going to try and use it. And here's some examples. A dictionary, and instead of using the add method, we're using put, and in put we are specifying the key and then the value. And then if we wish to access an element, we're using get. So here we're doing key value insertion. We're doing a traversal. The traversal looks kind of complicated here. We're extracting an iterator, calling next, and then we're extracting keys and values. Again, we'll be trying to simplify this, and in the next slide deck we will be attempting to explore how we don't need this typecasting here, which is a little bit worrying. Set realizes the set abstraction. It's closer to a list in a map. We're inserting things into the list. So we've got the same method, in fact, add. We don't really, though, have the notion of an iterator to march through the set. And if we insert the same element twice, then it won't be inserted. There'll be no duplicates permitted, and one will remain. So back to our forest picture, we can see the classes we've been touring here. That's our collection interface. It's in dotted notation. This is the list and the set we were mentioning. And then there's hash set, which we've looked at. And the one you've been using is array list here. I think in the first lab, we invited you just to take a peek at linked list and see if you could change to using a linked list instead of an array list, just for as an experiment. Now, how do you know which one to pick? Which one do you choose? Which one is most appropriate? We're presented with a myriad, apparently, of options here. Well, choice between map and collection is clear enough. Map gives you keyed access. If you don't want keyed access, collection is fine. Distinction between list and set is also pretty clear. If you don't care about how they're ordered inside the collection and you don't want duplicates, set is simpler and more matches closely your problem area. If you do want sequence, you want a first and a last, and you want to know where it is in the list, then you're looking at the list. Now, list, however, has multiple implementations, not more so than the ones I'm showing here. And choosing to select which one depends on the nature of your usage pattern and the desired performance you're willing to suffer. It centers around how often you're updating, whether it's write only, whether you're updating the list in the middle, at the end, or at the start, and various other potential patterns. We'll take a peek at those a little bit later on. However, this is all we need really for our purposes, and certainly for our module, we'll hardly venture beyond these ones here. That is, we hardly venture beyond the core hash set, array list, and hash map. Now, there is one exception to that. We may be interested in a little bit later on, either be independently or perhaps under our guidance when we look at some other examples later, some related interfaces in the framework around sorting and searching. And these interfaces, comparator and comparable, can be quite important. They're not a topic for today, though. Our topic for today is just to get an introduction to the fundamentals, and these are the fundamentals here. These core set of interfaces and classes. You're already using them. You're using ArrayList already, and I think you're seeing they're reasonably straightforward to use. Okay, I'll take another short little break, and then just 5 minutes this time, and then we'll get into our last session, which is a little bit more complicated, but we'll explore it in any sense. Okay, so I'll see you in 5 minutes, let's say.